Sure, we will start. So in the last class, we ended with the discussion on register. In brief, I have explained you register, type of register, shift registers and all. Right. Quickly, we'll see now how exactly we can construct registers. And I told the best flip-flop that can be used to implement the register is the D flip-flop. So we'll be seeing one important example of the register that is a 4-bit D flip-flop register with data load, clear, and clock inputs. Right? This is also an important circuit or the important example from your examination point of view. Also, it is there in your the question bank which I given for the third CI test. Right? So 4-bit register means you compulsory have to use 4 flip-flops. So here 4 D flip-flops are used, right? And then there are other connections shown here, right? This is flip-flop. This is the first flip-flop or the LSB flip-flop here, Q0. This is one flip-flop, second flip-flop, third flip-flop, and fourth flip-flop. Right. So we are indicated the inputs of these flip-flops as D0, D1, D2, D3, and the outputs of these flip-flops are Q0, Q1, Q2, Q3, and then common clock is applied to all the flip-flops. But you can see here, this clock is not directly given here. Clock is given through this AND gate, and this clock is ANDed with the load signal, right? So what is the significance of this load signal here? Whenever this load is active, that means whenever load is high, that time only the clock will be given to all the flip-flops. Otherwise, clock will not be applied. If you give clock directly, it will be available every time, all the time. But now since the clock is given through this AND gate and another input to the AND gate is load, so only when this load is high, the clock will be enabled, and whatever the data inputs you give, that will be loaded into the flip-flops. Basically, register means it will store what input you give. And we know that in D flip-flop, whatever input we give, that will be stored in the flip-flop, provided you apply the clock. So these data inputs, what you are given, in this case, I have shown the example like 1101. This will be loaded in these flip-flops, that is 1101, only when the clock is applied to these flip-flops. So how this clock will be applied to this flip-flop? So obviously, when you make load high, when you make load equal to 1, then only this clock will reach all the 4 flip-flops. And when the clock reaches all the 4 flip-flops, whatever the input you have given here, data input, that will be stored into these flip-flops, and the same thing will be available at the data out. Initially, we assume that all the flip-flops are reset. So initially, all the flip-flop output, that is Q3, Q2, Q1, Q0 is 0, 0, 0, 0. Right. So when you give the clock by making load equal to 1, this 1101 will come here. So this flip-flop output will change from 0 to 1. This will change from 0 to 1. This will remain 0, and this will also change from 0 to 1 because we have given input as 1101. Right? That is how this 4-bit register works. Then you may ask, what is this clear N signal here? I have not shown just clear. It is written as clear N because of this bubble. It indicates it is active low signal. That means whenever clear is 0, right? What happens? Can anybody tell me? What is the significance of this clear signal here? I explained what for load is used, clock is used, data input, data output, everything explain you. And I have shown how that 1101 is stored in the flip-flops. Now, what is the significance of this clear N signal? Yes, can anybody tell me? This clear N signal is used, as the name indicates, to clear all the flip-flops. That means whenever clear N is active, all the flip-flops output will be 0. So whether clear equal to 0 makes all the flip-flop reset, or clear equal to 1 makes all the flip-flop reset here. Yes, Shreya? You have to make this clear either 0 or 1.
Yes,
So
sir.
by what value of clear n makes all the flip-flop output 0?
Clear n. So 0.
Why 0? Why you
So
have to make it 0? When you make this 0 means everywhere you are applying 0 here.
0. Yes, sir.
0, 0, 0. So how by applying 0 all the flip-flop output will be 0? Because this is the additional input for the flip-flop. There are two additional input for the flip-flop. If you remember, which I explained in the earlier classes, clear and preset. If clear is active, the flip-flop will be made, flip-flop output will be made 0, and if preset is active, flip-flop output will be made 1. Now
Yes,
here you are making clear
0.
0. So this 0 will make all the flip-flop outputs as what?
0.
0. Why? Because of this active low input.
Input.
If
Yes, sir.
this bubble is not there, then you would have applied 1 to make all the flip-flop outputs to 0.
0.
Since it is an active low signal, 0 indicates it is active. So if you apply clear n as 0, all the flip-flop will reset. And if you make clear n as 1, then what happens? If you make it 0, all the flip-flop output will be 0. But if you make clear n as 1, what happens? Is it all the flip-flop output will become 1? No. All the flip-flop output will not become 1. So when clear is not active, that means when clear is 1 and if load is active, the clock will be applied to all the flip-flop, and this data input what you have given will be loaded into each of the 4 flip-flops, and the same we will be getting it as the output. And this is how the 4-bit shift register, 4-bit register works. That's what is mentioned here. You can just go through it. When load is 0, the register is not clocked and it holds its present value. And when load is 1, the clock signal is transmitted to all the flip-flops, and data applied to the D inputs will be loaded into the flip-flops on the falling edge of the clock. Can anybody tell me why falling edge of the clock? Again, you can see here the clock is shown as negative edge triggered clock. Okay, so that is about this. The same thing is again explained how this input 1101 is loaded. If the Q outputs are 000 and the data inputs are 1101, after the falling edge of the clock, simultaneously all will be loaded, because parallelly we are loading into each of the flip-flops. So in single clock cycle, all the flip-flops will be loaded. In this case, the flip-flop, first flip-flop will be loaded with 1, second flip-flop also will be loaded with 1, this will be loaded with 0, and this will be loaded with 1, so that finally we get the output as 1101, right? So that is the first thing, so example of the register we have discussed, right? So now if you don't want to use the AND gate to enable the clock and the load signal, normally every flip-flop will come with one more input called clock enable. So instead of having a separate load signal and then use AND gate and both you AND and give it to this, the clock can be given directly to all the flip-flops, and this load signal itself can be given to the clock enable like this. You can see here. The previous circuit and this circuit are same. The only difference is the flip-flop is having one additional input called clock enable. As the name itself indicates, whenever you apply the signal to the clock enable, then only whatever clock you have applied to the flip-flop will come into picture. So again it is same. Instead of using a AND gate, two inputs are directly given to the flip-flop. One, that is the clock, and the other is the load as a clock enable. So the functionality of this flip-flop also remains the same. So this also is a 4-bit register with the clear and load signal. The same thing is indicated here symbolically. You can see it is that dash, this 4 indicates it is a bus notation. Q is 4-bit, this D is also 4-bit, then clock is applied, load signal is given to clock enable, clear signal is given to the clear input. This is the symbol of a 4-bit register using bus notations. Okay. Right. Then this is one more example how the data transfer between register can take place. In this, it is explained that how the data can be transferred from the output of one of the two registers into a third register using tri-state buffer. Right. So here we have shown two registers actually. This is one register, register A, which is of 2 bits, that is indicated by A1 and A2. This is register B again of 2 bits, right? Which the 2 bits of the register are indicated by B1 and B2. And each the register flip-flop will have a buffer here, tri-state buffer. That means what is available in this flip-flop will be made available at this point only when this buffer is enabled, because already you have studied the tri-state buffer. So what we are doing is this flip-flop A or flip-flop B output will be loaded into, the register A or register B output will be loaded into the third register. This is the third register. Either this or this will be loaded depending on the enable as well as the enable signal. If enable is 0, right? So if enable is 0, what happens is a register, if enable is 1, this value will be loaded, register A will be loaded in the third register, that is register Q, and if enable is 0, the register B will be loaded into the third register, that is register Q. So obviously it is written if enable 1 and load is high, output of register A is enabled onto the tri-state and that will be loaded into the Q. Similarly, if enable 0, load is 1, then register B will be loaded into that output register Q. Okay. So this is the logic diagram for a 4-bit register with tri-state output. That means we have shown here 4-bit registers, not 4-bit, 8-bit registers, Q1 to Q8. And then we have added a tri-state buffers. Means what? These data will be loaded into these register when clock is active, but this will not be available to take immediately for the next part of the circuit. That depends upon this enable signal. If the enable is high, then only the output of these flip-flops, that is an 8-bit register, will be available for the output, right? This is data transfer using tri-state buffer, the same example which I have earlier explained, same thing is shown. You can go through that. Okay, the next one more important question from this part, parallel adder with accumulator. Now what exactly you mean by parallel adder? Right, already you have studied full adder can be used to add 2 single bit number along with the carry. But when you want to add a multi-bit number, then you have to use group of full adders, and you have to connect these full adders in cascade, and you can add multi-bit numbers, 2 multi-bit numbers with or without carry. So that arrangement of cascaded full adders is called as a parallel adder. Now to this parallel adder, we are adding a flip-flop to store the output. If you add flip-flop to store the output, then that parallel adder is called as parallel adder with the accumulator, and here the group of flip-flops which we are using for each full adder to store the output of the full adder are called as the accumulator, because the result can be accumulated there. So this is the logic diagram for the full adder or parallel adder with accumulator, right? So here you can see that we have shown the input, 2 inputs are there, x and y, where x1, x2, x3 up to xn is one n bit number and y is another n bit number. We want to add these 2 numbers x and y, and we have to store the result in the register. So actually we have to perform x plus y, and that result has to be stored into these group of flip-flops called the accumulator register. So what we are doing here is x, initially we are loading into these flip-flops, so that to this flip-flop, whatever the y is there, one input to the full adder, we are giving from this. You can see the output of this flip-flop is given as an input, output of this flip-flop is given as an input, output of this flip-flop also given as an input, this. So one input to the full ladder is from the flip-flop and another input to the full ladder is directly given. Another input to the full ladder is directly given, that is Y. So what you need to do is this X is initially stored in the flip-flops, that is accumulator register, and then that is given as input to the full ladder to this X. From the accumulator register, Y is added, and once you add this Y to the X, whatever result you get, this result will be again stored into the accumulator. So it is like we are performing in effect X equal to X plus Y here. In effect, we are performing X equal to X plus Y, where X and Y are the two n-bit numbers. So again, I am repeating, first n-bit number X is stored in these flip-flop called accumulator register. Another n-bit number Y is given input to the full ladder. So these two will be added, and when this X1 and Y1 along with the input carry 0 is added, you will get sum 1 and the carry 2. So this sum 1 will be stored in this flip-flop and carry 2 will be given to the input of the next full ladder. So this full ladder will add X2, Y2 along with this C2 and it will get S2. That S2 will be stored in this flip-flop and C3 will be given to the next, and this process will be continued, and after the n clock pulses, we will get the result of sorry, not n clock pulses, because it is a parallel. All flip-flops will be working in parallel. So when clock is applied, the outputs of the flip-flops are given as input to the full ladder, and another input will be given from the Y, and both will be added, and in single clock cycle, both X and Y will be added, and the result will be stored back in these group of flip-flops called the accumulator register. So I hope it is clear. This is like a register. In this register, first X is stored, and then bit by bit you are giving as input to this group of full ladders. So if you are adding two n-bit numbers, you need n full ladders here. So you have to show n full ladders. I have shown only 4 here, so it doesn't mean that only 4 full ladders can be used. You can have any number. N can be either 2, 3, 4, 5, 6, up to any number you can take, and those many full ladders you have to use, and you can add the numbers. So that is the second important part from this register. I hope this is clear. Right? If you are having any difficulty doubts, you should stop me in between and you should ask. Okay? So that's what I have already explained. And this is the symbolical, this one more is like n-bit parallel adder with accumulator using what is called as a mux, right? So here you can have X can be taken from this flip-flop and given as an input, Y is the additional input. So it will perform X plus Y and it will give this sum, and that sum will be stored into the flip-flop, right? But here we are using now two signal, add and load. When you use load, like this will be loaded into the flip-flop, right? This will be loaded into the flip-flop, and when you give add signal, these two will be added. Load means this you are loading here into the flip-flop, and when you give the add, this and the flip-flop output will be stored. So this is n-bit parallel adder with the accumulator. Okay, that is regarding the register. So two important questions I already given. You have to prepare, and I have explained those also. Right. Next, shift register also in brief I have explained in the previous class. The register who has the capability to shift the bit stored into it either to the right or left one bit at a time is called as a shift register. The bits can be shifted out from one end of the register, or it can again, the shifted bit can be thrown out of the register, or it can be added into the register from the other end. Depending on that, we have the different shift register. So these are the different types of shift registers which are explained here. One end data is entering, other end data is going. Such type of shift register are called as what? Serial in, serial out shift register. Right? Both these are serial in, serial out shift register. One data is shifted from this end and out from this end. Here it is entering from this here, it is going from the other end. So that is serial in, serial out shift register. Here you can see you are inputting the data simultaneously. So it is called as parallel in. But output you are not taking simultaneously. Output you are taking one bit at a time like this. So it is called as parallel in, serial out shift register. Similarly, here you can see data is entering from one end bit by bit, and you are reading all the data outputs simultaneously. So it is called as what? Serial in, parallel out shift register. Similarly, if you enter all the data bits simultaneously and if you take the data out simultaneously, it is called as parallel in, parallel out shift register. And here shift register, whatever bit you are shifting, you are giving back. Such shift registers, we can call it as the cyclic shift register, both. From this end you can put, or if it is going from this end, you can enter it from the another end. So this type of shift registers are called as cyclic shift register, where actually the rotate operation takes place. Whatever is stored in it, it will be rotated and it will come back again from the other end. So in such cases, what happens here is, whatever you are entering from one end, other end it will go, it will vanish only, it will not come back. But in this case, what happens? Whatever you are shifting out, that will come back again from the other end. So that's why those are called as the rotate operation. And that is the main difference between shift operation and the rotate operation. Right. Now this is the simple shift register, right shift register is explained here. The serial in, serial out shift register. In fact, this you already studied in your first year engineering also. So how exactly it works? Whenever you apply, initially we'll assume that all are 0, 0, or you can assume anything. Initially, I will assume all the flip-flops are stored with 0, and now whenever this shift is high, and if you apply the clock, what happens? Whatever serial in bit is there, that will be loaded into this, and the output of this will come here, output of this will come here, output of this will come here, and what was the previous stored here, that will go out. That is serial out. So whenever you enter one bit, that will come and sit in this flip-flop. But earlier, what was there in this flip-flop? That will go here. From here, what was earlier? That will come here. From here, the earlier value will come here, and the earlier value of this flip-flop will go out. That is called as serial out. So you are giving data bit by bit from one end, and it is going bit by bit from the other end. Such type of shift register is called as serial in, serial out shift register. The same operation of this serial in, serial out shift register is explained with the help of timing diagram here. You can just observe this. This is very important. We are shifting, say, 0, 1, 0, 1. So I want to enter in this shift register 0, 1, 0, 1. So first, at the first clock pulse, you have to enter 1. This 1 should come here, right? Then you should enter 0, then you should enter 1, then you should enter 0. So after 4 clock pulses in this shift register, you will get the value 0, 1, 0, 1. How exactly it happens? You can see here I have shown step by step. Initially, I will assume that all the flip-flop outputs are 0. Initially, I am assuming, that's what you can see here, 0 or 1, anything you can take. Initially, all the flip-flops can be assumed either as 0 or as 1, right? And now, the serial input SI, okay, initially I am not assuming it as 0, 0, 0, 0. They have taken initial as 0, 1, 0, 1. 0, 1, 0, 1. This is what I am assuming initial value, right? Initial value is 0, 1, 0, 1, and that's what is shown here. You can see this is Q3 is 0, this is 1, 0, 1. You can take initial anything. As I said, you can take all 0, all 1s, or any value. But now what they have told is initially it is 0, 1, 0, 1, and now you have to load 1, 1, 0, 1. New value that you have to store into it is 1, 1, 0, 1. So how you can do this? First take this 1. First take this 1 and give it as an input here, right? You can see, and then apply the clock. Fine. Okay, sorry. Yeah, clock is applied. So at the rising edge of this clock, what happens? You can see there. The shift register also SI you have given 1. This is SI that you have made 1. So you can see what happens to Q3. Q3 becomes 1. Q2 becomes, what is the earlier value of that will go into Q2. You can see that shift operation is happening there. How that shift operation is happening, that is shown there. This is at the first clock pulse. Then at the second clock pulse, you can see what is happening there. At the third clock pulse, you can see what is happening. Then the fourth clock pulse, right? At every clock pulse, shift operation will take place. The value from the one flip-flop will go into the other. This process will continue, and after the 4 clock pulses, whatever the value you want to load, that is 1101, will go. At every shift operation is explained. At the first clock pulse, 0101. Then at the 0101 is the initial. At the first clock pulse, it become 1010. Then it become 1101. Then 0110, 1011. Right. This is the register. This you can do it as a homework. One example is given here. I'll share these PPTs to you at the end of the class. So I want you people to do this. In fact, it is explained everything, just to go through it. Only difference here is we have used negative edge triggered clock, serial in, serial out. Okay. So some of the examples are given. You can self-explanatory examples are there. You can go through it. I will not spend time on these. See, everything is very nicely explained there. Self-explanatory things are there. And this is what is called as cyclic shift register or the rotate operation. Whatever bit is going out, if you want to bring that back, then you can connect this serial output back to the serial in. Once you load the 4-bit value into it, the same thing will be rotated again and again when you go on applying the clock pulses. Such shift registers are called as cyclic shift register. Right. This is very important from your examination point of view. They'll ask you to explain the 8-bit serial in, serial out shift register using SR flip-flop here. You can see here SR flip-flop, how we have used. The input is directly given to S and the complement of that is given to R. That means effectively we are using this SR flip-flop like D flip-flop. If you remember, if you give input directly to the S input and complement of S, you are giving it to R, then that flip-flop behaves like a D flip-flop. And exactly the same principle is used here. Instead of using D flip-flop, SR flip-flops are used. So give directly one input to S and the complement of that you give it to R, it becomes like a D flip-flop, and the same functionality you are going to get. You can give serial in, serial out. Only difference here is, as I say, we have used SR flip-flop instead of D flip-flop, and the functionality is similar to the D flip-flop. Right, at every clock pulse, whatever you give as an input, that will be loaded into it, and when you apply the clock, every bit will be shifted 1 bit position and you will get the output. So the same operation what I have explained here, same thing is applicable for this also. But the difference is we have used SR flip-flop. But effectively that SR flip-flop is used like a what? D flip-flop. And one important thing you should remember in all these counters register is that this flip-flop will be the LSB flip-flop, that is Q0, and this will be the MSB, that is Q7 if it is a 8-bit. Right? Serial in, serial out, and this is shift register, parallel in, parallel out. It is rarely used. Then one more is like a universal shift register, which can have a different functionalities is shown here depending on this SH shift enable, load enable, serial in, parallel out. So when shift is 0 and load is 0, there will not be any change. It will retain the value what is there. When shift is 0 and load is 1, what happens? Whatever you give the input, that will come into this 4-bit register. And when shift is 1 and load may be anything, then it will perform the shift operation. So how it performs the shift operation? At Q3, this value will come and then all will be shifted and Q0 will go out, that it performs the right shift operation. That means it is performing the three different operation: no change operation, load operation, and right shift operation, depending on the value of these two signals, that is shift and load. And of course, all this operation takes place with respect to what? The clock. Okay. The same is shown implementation using muxes, right? Then this is the timing diagram for the mux. It is shown the timing diagram for the shift register, how it shifts from one bit to another bit. That's what is shown here, depending on what you take. Here initially we have taken all 0, and then we are trying to insert 1 0 1 1. Right? These timing diagrams are very important. Whenever you are explaining counters, shift registers, compulsory you have to draw the timing diagram, otherwise you will lose the mark. You have to draw the block diagram, and you have to write or draw compulsory the timing diagram. Without timing diagram, your answer is incomplete. Okay, that's what shift register. Okay, then ring counter. So what exactly you mean by a ring counter? So initially we will be loading some value into the flip-flop, and the output of the last flip-flop will be giving back to the first flip-flop. Right? Output of the last flip-flop, if it is given back to the first flip-flop, then it is called as a ring counter. But one drawback of this ring counter is, suppose if initially I make all these flip-flops 0 0 0 0, and if you go on applying the clock, any number of clock pulses you apply, every time you are going to get the output as 0 0 0 0 only. Hence, when you are implementing a ring counter, maybe you are doing this in your laboratory also, when you are implementing a ring counter, compulsory the LSP flip-flop or the MSP or LSP, any one flip-flop, output should be 1. Compulsory it has to be 1. Otherwise, what happens? Every time you are going to get the output as 0. Now, if you make this 1 0 0 0, if you apply the clock, this 0 will come here, then this becomes 0. This 1 will come here, then this 0 will remain. So initially it was like 1 0 0 0. At the second clock pulse or the first clock pulse, it become 0 1 0 1. Then if you again apply the clock, this 0 will come here, this 0 will come here, then earlier 1 will come here, and this 0 will come here. So you will get the output as 0 0 1 0. Similarly, if you apply one more clock pulse, this 1 will shift here, and then all other become 0, that is 0 0 1 1. Once again, if you apply the clock, this 1 will come and sit here, then these become 0 0 0, and the process continues. So after 4 clock pulses, you will get again the original value. So such counter or such shift register is called as a ring counter. But I have told one drawback of this is compulsory you have to make one of the flip-flop outputs should be 1. If all flip-flops are say like 1 or 0, then the same thing you are going to get again and again when you apply the clock pulses. So that should not be done. That is what is called as ring counter. So the problem of this ring counter is overcome in what is called as Johnson counter. So what is the Johnson counter is, instead of giving the last flip-flop output to the flip-flop, we will give complement of last flip-flop output to the first flip-flop. So advantage of this is, now what happens, suppose if initially I take all flip-flop as 0 0 0 0, and now if I apply the clock, instead of coming this 0 back here, what will come now? Since we are connecting this complement output, what will get? Can anybody tell me? Initially I have taken all flip-flops as 0 0 0, but now I have not connected the Q output of the flip-flop back to the input. What I have connected is Q bar, right? So what you will get here, if this is 0 now, what is this? Yes, what will be this? This will be 1, and this 1 will come here. So automatically the problem of making one of the flip-flop set will be overcome here in the Johnson counter. You can see serial input, you can give anything now, right? Initially if it is 0 0 0 0, this 1 will come here, and then we'll get 1 0 0 0. Again 1 0 0 0 means next again 1 will come, it becomes 1 1 0 0. Next it becomes 1 1 1 0. Then fourth clock pulses, it becomes 1 1 1 1. So after the 4 clock pulses, it becomes 1 1 1 1. Now if you apply the fifth clock pulse, this 1 we are not giving now. What we are giving? Complement of that 0. So this 0 will come here now. So 0 will start entering from the other end. So it becomes 0 triple 1, then 0 0 1 1, triple 0 1, again 4 zeros, and then the process repeats. So here you can see that initially we started with 0 0 0. Again we will be reaching 0 state after 2n clock pulses, where n is number of flip-flop. Here how many flip-flops are there? 4. So after 8 clock pulses, again we'll reach back to the original state and the process continues. Hence this particular shift register or the Johnson counter is also called as mod 2n counter. Sometimes they will ask the question, justify mod, how Johnson counter is called as mod 2n counter. So you should be able to do that. So that is about the Johnson counter, right? This is what is shown here, Johnson counter, how it works with the help of transition graph. So in general, I have explained you shift register, right? So that is about the register part. One more small part is left in this module 5, that is called as state table and state graphs. I don't want to explain that now. Maybe after your third CI test, we need one more class. We'll study this state table, state graphs, Moore and Milli machine, and what exactly is the difference between Moore and Milli machine, and we'll see how these Moore and Milli machines are implemented. That is the last part of this module 5. I need one more class for this. That we'll do it in the next class after your test. So as I said already at the beginning of this class, till the shift register portion you are having for your third CIE test. Yes.